Hello, my name is Brandon Bailey. I work at the Aerospace Corporation within the Cybersecurity and Advanced Platform subdivision. And I'm here today to talk to you in the Aerospace Village about some research around hunting for spacecraft 0 days using digital twin technology. On the front page here, there are several links to other publications and YouTube videos around cybersecurity in space. So if you're into space and cybersecurity content, just go ahead and click those links and watch those videos and learn about some of the other work that we've been doing here. But specifically today, we're going to focus on testing and doing research on spacecraft software using digital twin technology. So what's the problem statement we're looking at here? So essentially, we feel like there's insufficient cyber testing of spacecraft technology. And there's a lot of factors for that reason. So space systems are system of systems, and they're tied together. And we're seeing people get more involved in space, and the cost barriers are being lowered, and the technology is evolving fast. And we're seeing new commercial ventures being forged, and therefore we're seeing a lot of kind of commercial off-the-shelf technology and embedded Linux and things that we didn't see in the past show up, but we're not seeing the security testing really where we feel like it should be given the threat environment we're in. So we're seeing more and more people being involved in space, and we're seeing different types of solutions being created, and we're not seeing that the threat emulation and adversarial based testing is not really keeping up with it. And speaking of the threats, people that are probably listening to this have awareness of the attack that happened in February with the Ukraine-Russia conflict with Viasat and the malware wiper software called Acid Rain. And there's a link here that you can click on that was produced by SentinelOne, and there's many others, but this is a good one that has information around this attack and what it was. So that was a ground-based attack, wasn't a spacecraft attack, but it was on an embedded system, I believe a MIPS processor on the SATCOM terminal. So the legacy assumptions that we have, that many people have about space technology and on the ground or the vehicle being somewhat not being a target of cyber attack, is kind of a misnomer at this point. So we're seeing this actively today, and we predict we're going to see it actively in the future. So one of the key, if you read the papers and links on the front of the paper, and we have a slide or two at the end, talks about defense in depth and the techniques that are needed to protect space systems on the ground and on the vehicle. We believe in defense in depth, and we think that the government, industry, and international community all should kind of adopt that defense in depth paradigm. But one of the key aspects of defense in depth that sometimes is overlooked is the verification and validation of the security implementation or the testing. So historically, spacecraft testing has really been functional based testing, where you're trying to determine, does it function this way or that way? Does it meet this requirement from a functional perspective? But there's not a lot of the cyber resiliency testing or adversarial based testing that we feel like is needed to keep up with the evolving threat. So to ensure these architectures and software are built with software and security resiliency in mind, we really need to think about ways to do this testing that could enable that type of adversarial based testing. And we think that digital twins, if they're built for that purpose, can really be beneficial and help out solve this problem. So ensuring that our current and future space systems are cyber resilient, it's going to be critical for national security and capability for the country. So what are some of the current gaps we see with security testing of spacecraft technology? So the physical spacecraft is typically, the flat sats that you see, or the satellite once it's assembled. It's a lot of the specialized hardware. It's expensive. It's somewhat cumbersome to deal with if you're trying to do testing, and there may be some limited availability on the actual asset itself. So they don't build 5, 10, 15, 20 of these flat sats or security or test strings to enable everyone access to do the proper testing. So we feel like if we digitize that, we can work on this in parallel with the development and help discover some vulnerabilities. So security testing, as I said before, is functional based, and it's often a lower priority. So the functional based testing, the verification and validation testing that really focuses on the functions of the spacecraft, that usually takes priority. The spacecraft, if there are security testers on staff, they typically get put at the end of the testing life cycle. And then sometimes they get booted altogether. I've seen where you get 2 weeks, you'll get maybe 2 weeks near the end of the testing cycle to do testing, and then the functional testing is slipped to the right a little. So your security testing timeline gets compressed and you can't do as much as you would like. And sometimes we also see as many of the existing simulators that you have in these test environments aren't really suitable for advanced cyber testing. So they're kind of like dummy simulators where you give it an input, you get an output. It's kind of stubbed, where it's not high fidelity. It's not actually running the software as it intends to run in space, which really doesn't allow you to test out, exploitation and do your exploit development and that type of thing. So, and one of the key things about security testing that we really need to consider is security testing is really exploratory in nature. It doesn't follow, in most cases, traditional step-by-step model where it says run step A, then step B, then step C. It really is more exploratory. It's trying to figure out what combination of inputs can break the system and cause some sort of damage to the system. So that doesn't fit well with a lot of the testing strategies that we've seen in the traditional sense for like a waterfall development in system engineering, where they expect the test procedures to be fully scripted and scripted as in like, step ABC. So you need to have an environment that has ample capability as well as an environment that has high availability so that you can do this exploratory testing. So we feel like the evolution of digital twinning with embedded electronics using technologies like instruction set simulators has the ability to produce these bit cycle accurate software versions of complex spacecraft that can enable us to do the testing that we want to do. So a fully functional software-based simulation can be scalable and accessible from anywhere by leveraging containerization and virtualization. You can put it in the cloud, you can run it on laptops. There's a lot of places you can do testing when you have these software-based digital twins that are high fidelity. And as the digital engineering ecosystem explodes, you can definitely see where this could help in that area. So you could have these digital replicas in your environment, in your digital engineering environment. And so as new cyber threats evolve with nation states, insiders, supply chain, we really have to think about how we can figure out how to outpace the discovery of these vulnerabilities and discover these ourselves and correct them. Because do we really think that the technology that we're using today that was built 10, 15, 20 years ago is free of vulnerabilities, or do we feel like it's just the vulnerabilities haven't been found yet? And I tend to think it's more of the latter, where you have technology that was built 20, 25 years ago, and just we've not had the security researchers really pounding away at those to look for these vulnerabilities. So we need to start doing that now and make sure that's part of our future strategy moving forward. So if we just go with the status quo and don't do the cyber testing with the APT emulation or threat emulation, and we don't do enough research in this area, we're just going to keep the status quo. It's going to lead to many failures in the future, in my estimation. So what is a digital twin? I've said the term a few times leading up to now. So what am I talking about? I've seen this presented in presentations and conferences about, hey, look at this digital twin I have for the space system. It has these boxes on a chart with these arrows and things, kind of UML-ish. That's not what I'm talking about when I talk about a digital twin. So what I'm talking about is it's definitely not boxes on the PowerPoint slide. It's not UML diagrams. It's basically not anything on paper. So what I'm talking about aligns with more with what Gartner says, and there's other definitions out there. This is just a good one. And so this is a digital twin is just a digital representation of a real world entity that encapsulates a software object or model that mirrors the unique physical operation process of the system. So it's important to understand what I'm talking about is basically ensuring that the software that you would run in space is the same software that you can run in your digital twin. You don't have to cross compile it. You don't have to make it, a Linux version or a simulated version. You take the same binary that you fly on your hardware and you run it in your digital twin environment to do your testing. That's what I'm talking about. So for the space system, in my definition, a digital twin is really a full digital representation of the ground and the spacecraft using only software. But you can say mostly if there are maybe hardware some components that you want. But if you can do it with only software, that's highly recommended because that significantly increases the features and capabilities of the digital twin. So if you've been involved in the space community and have done testing and have been in the labs that go through the halls of these development organizations, you'll see things like this. You'll see CPCI backplanes. You'll see 1553 cards. You'll see serial. You'll see big racks. So what I'm talking about is basically taking all of those physical devices, turning them into ones and zeros, and making the spacecraft run on a laptop, in a cloud, in a digital environment. That's the goal, is a full digital representation of that spacecraft system or space system and being able to do the testing. How do you do that? Well, borrowing some terminology from a group I used to work with within NASA, the Independent Test Capability team, in this presentation, we created a term back then called simsmithing, which was basically the process of creating software-only simulators using paper, using mission artifacts, ICDs, manuals, requirements, whatnot. So the goals of the simsmithing process was basically build a software-only simulator because you could reduce costs and don't have to duplicate a bunch of hardware. You can build, you can maybe reuse simulations from across other development organizations that may be developing sims that are the fidelity you need. You can bring it into your own environment. So you want your flight software to believe it's running in space on the same hardware. So how do you do that? You take the words on paper, you kind of digest them, you build your thing, and you certify it. And how do you certify it? The way we certified it, it's probably a strong word saying certification, but the way you would validate that the digital twin is accurate is we would typically take the same tests from the development organization that's developing the spacecraft and run those same tests and get the same results, and then that would be a mechanism to validate. So we wanted to be able to provide take the same ground scripts that run within the ground system and basically run those and get the same results, and then we felt like our system was validated. So turning words into high-fidelity simulation that enables an adversary threat emulation for cyber attacks. That's what we're talking about when we're talking about simsmithing specifically. So what's an example of a digital twin architecture given the context of what I'm saying? So some of the key components, if you want to do this the right way, in my opinion, is you want to use the same ground software so that you have the same test driver as the operational system. So that would mean whatever that ground software looks like, you want to include that in. You want to have an emulated embedded hardware. So if you're using, for instance, like a PowerPC 750 or an ARM, you want to have a digital representation of that. You want to take the unmodified flight software binary and you want to run it on that hardware. And you want to integrate cyber tools if you have them and need them, like fuzzing harnesses and things like that. You want to bring in the appropriate physics models as well to ensure that you have a dynamic simulation, because you want the flight software and the software under test to think it's in space operating in orbit. So pictorially, what does that look like? So here's the ground driver or simulation, ground system test driver, and you may have cyber tools that you want to integrate there. And then you have the space to ground link. So that could be RF if you want it to be. It doesn't have to be. Depends on your goals of testing. If you're trying to do RFI, radio frequency intrusion or something over RF link, then you need the actual RF. But typically, if you're focusing more so on the flight software itself and trying to find 0 days on the spacecraft, you don't need the RF link. You can just do a UDP or a TCP/IP link and connect over Ethernet from that perspective. So what's the flight data system look like? It looks like, so you probably need some sort of virtual backplane middleware that mimics like the CPCI backplane. You need your main onboard processor. So that could be, PowerPC 750, it could be some ARM. And then you need your obviously flight software, which is usually the thing that's under test, running there. You need hardware models if your system needs them, like 1553, SpaceWire, whatever you're trying to do from that perspective. What other peripherals do you have? You want to do that. So and then you want the space dynamic simulator if you need one. So that would be that's where you model the physics of the spacecraft and have it do its thing. Maybe you need external simulators. A lot of times you can get those from the development organization developing the spacecraft. They may have external sims that you want to integrate in. It's not a requirement. Every now and then you may have real hardware that you want to integrate in for various reasons. You can have those plug into the middleware backplane, and then you can have cyber tools and bus monitors and things on your system if you need them. So not every digital twin needs all these components, but as we'll show in an example of this, but this is just kind of a representative example of what you would expect a spacecraft or a space system digital twin to really look like. So what's some benefits of this? If you think about how we typically develop software and develop space systems, you have to fabricate the hardware, and then you can start your software development as the hardware becomes available. And that creates this serial-ish type of process where you fabricate hardware, get the software, then do the testing. If you develop these high fidelity software only digital twins, you can significantly shift left the entire process. So you can start fabricating, you can have your hardware being fabricated, but you also have digital representations of that hardware that your software guys can actually start doing software on. So you can shift left the discovery of vulnerability, shift left discovery of bugs in general, and save time and money in the end. So that's kind of what you're looking for here is trying to shift left that development life cycle so you can find the vulnerabilities and 0 days and things on the system using these digital twins. So dynamic analysis in general using digital twins is a unique approach to think about how you examine the software, looking for 3 principles. So what you're kind of trying to do is does the system or software do what it's supposed to do? So that's the functional must occur behaviors. But then from a security perspective, you want to ask a couple other things. I want to ask, how does this thing act under adverse conditions, and how does it not do what it's not supposed to do? So what must not occur on the system? So those are things that are more aligned with the security aspect. You may have some, so the traditional testing really deals with that first element where what must occur, and then you think about security as the secondary ones. Digital twins can be a very good test environment to test out those second behaviors there that are listed. Because 0 days typically live in that area. They live in the area where things, how you give it some sort of adverse condition, or you try to exploit it to make it do something it's not supposed to do. So what are some other benefits other than just kind of security and 0-day testing? So obviously the pen testing is the big benefit, one of the big benefits, which is listed here. You can use these simulations to do red versus blue events, and so you're not actually using real hardware. So this is where things like Hackasat or red versus blue or a red flag or things like that really help having these things available. Spacecraft operator training is a good one. So you can give people hands-on experience with the actual ground system and software to do their kind of training. And one of the things as we start to expand the artificial intelligence and machine learning capabilities in the space domain, we see that there's a lack of realistic spacecraft TT&C data that's available to people for various reasons to do the AI ML training. So with the digital twin, you're going to get the high fidelity telemetry and TT&C data that you want, and you can inject faults and things like that in the system and help train your models a lot better than and with a lot more high fidelity data. So that's a good feature as well. Having these, you can give these digital twins to your AI ML groups to get the TT&C data that they're wanting to. From a DevSecOps perspective, this is a huge benefit if you're kind of not aware of some of the limitations that you see in the DevSecOps arena. When you're dealing with embedded systems, the DevSecOps, in the traditional web application world, DevSecOps is pretty easy with the automated continuous integration and deployment. It's not so easy with actual in embedded systems. So you need high fidelity emulators that you could run those full regression suites against automated. So if you had a good digital twin, you could essentially run full test suites overnight of the system of systems test, as opposed to just unit test. And you can also dry run hardware and software changes using these. If you have some sort of bug fix, you want to test it out in your code base, you check it in, have it run through, see if it works, and then go from there. So it really speeds up that DevSecOps process. You can have full CI pipeline with operational ground software and the spacecraft software running every night, which is a huge benefit, which people don't necessarily understand how big of a benefit that really can be. You can actually use it for flight software V&V. So right now, you see, people that do their verification validation testing on the hardware, and they're kind of limited to doing that. Now, you may not want to do formal verification buy off of requirements using a digital twin if you're not that comfortable with it. So what you can do if you don't want to do that is you can use it for the dry running. So I know numerous times when I was doing some testing on some of the spacecraft, in my time at NASA before I came to aerospace, was we would hear stories of people that were just chewing up all the time and availability of the test assets, dry running and debugging their test scripts that they're using. And so that limited availability for other people. So if people had the ability to have a digital twin on their desktop to dry run all these test scripts using the same ground system software as they're going to use for the run for record, huge benefit. It relaxes some of that availability issues that we see on these assets. Another thing was when you have something like a pandemic, like we had over the last couple of years, where people weren't allowed to go into the lab environment necessarily, and they were all teleworking. If you had digital twins during that time for your system, you could be working from home. You could maybe rehost those digital twins in the cloud, because a lot of the labs and things you see in the spacecraft world aren't necessarily internet connected for good reason. So getting remote access to those is very difficult. So if you had these digital twins in your environment, you would be able to actually test the hardware and things of that nature, fully remotely, and test out, all this stuff in your digital twin environment. Operational day and life scenarios. I've mentioned this about early operator training to show people how this works. You can also get your mission defense people their training using real spacecraft, so they can see how the actual data flows. So not only your operator training, but your security operator training. If you have MDTs or different types of people that are expect to monitor the security posture of your ground infrastructure, giving them the availability to work with these digital twins and see the TT&C data flowing in a simulated mock environment, to give them exposure to these and not just learn on the job, what could be hugely beneficial. And one of the big things I alluded to earlier is fault injection. And if you have this hardware that costs hundreds of thousands of dollars or millions of dollars, you may be reluctant to try certain fault conditions. And in a digital twin, you have a much easier way to do fault injection. You can fail CPUs, you can test component failures, you can simulate stuck thrusters, you can do all sorts of simulation to see how the flight software responds without risking the hardware for damage. So that's a huge, big bonus as well. So when you go software only, what are some of the other things that you can actually do or benefits you can get? So affordability. So spacecraft hardware, like I said several times, is usually really expensive. So thousands to hundreds of thousands of dollars. And if you need to replicate another string, say your availability is low on your test strings and your FlatSat, you can't just create another one out of thin air, right? You got to procure that hardware, you got to build it. It's months on end. So you're looking 6 months or longer to get a full, FlatSat up and running, more than likely, if you have to procure it all. The digital twin, it's only a function of your computational resources. So like, say you have a couple of digital twins, and now you hire new staff and they need their own, just spin it up. It's all virtual. So you can just create another one with no problem. It really shortens that down, and it's cheap because you don't have to buy more hardware. It usually fits in your same compute footprint. Scalability, and when you're 100% digital, you can replicate as many of these as possible. And if you start thinking about where we're going with peripheralated LEO constellations moving forward, how are we going to be able to test, laterally moving or attacking a constellation and moving in a PLEO environment? Are we going to have 50 different hardware strings of FlatSats kind of inter-network together? Probably not. You're going to need some sort of digital representation to do that testing. So this can really help in that area as well as we move towards PLEO. Usability is often something that is much better for debugging. Is you don't always have the capability. Some systems they don't have JTAGs. You definitely can't pause, rewind, and that type of thing when you're dealing with hardware. But in the software world, you can definitely save states. You can pause. You can do things like that, which is cool. If you've ever played these digital twins are kind of like Nintendo emulators and Super Nintendo emulators. If you're kind of into the gaming area, so It used to be, you know, back in the 80s and 90s, we had to have a physical NES, Nintendo Entertainment System, and it was a hardware thing. We put the cartridges in and we played. And if you played those, there was no pausing necessarily the state and restoring later. You know, you had to play all night or you left it on and come back the next day. In an emulated world, you know, with NES emulators, if you play those, you can actually pause and it freezes the entire hardware setup and where you're at in the game and that type of thing. So if you think about the benefits of that from like the gaming perspective, is like, oh, okay, well now I can restore the state from where I was before. You can do the same thing from a spacecraft testing perspective. Say you want to simulate something, you know, 30 days into the future because your mission is, all right, 30 days in, I deploy, you know, like for it's like James Webb or something would, you know, over so many days it deploys unfolds multiple areas. So if you want to simulate that, simulate multiple days in advance and then restore to that, using digital twins is one of the only ways to do that. If not, you're a burden of real time, and you can usually speed up and do things quicker and then pause, restore, and rewind, which is a huge benefit. Availability, mobility, it's easier to distribute these things or remote collaboration, and you can leverage it at multiple classification levels as well. So sometimes in the security domain, certain tactics, techniques, and procedures may be, you know, more protected than others. So you can have digital twin replicated at multiple classifications level. You can have unclass, secret, TS, whatever you want. And if you build it cloud native, you can host it in those environments too. So that could be a huge benefit, because it's a very mobile. So how do we build these things? What does it look like? What kind of technology do you need? So, you know, 20 years ago, the technology wasn't necessarily there. We didn't have the technology to do the instruction set simulation, to build out a PowerPC 750, 401, Leon 3, ERC 32, or something like that. Standard x86 binaries is much easier, right? A Windows device, you know, you have VMware, you have Docker or Kubernetes, you have all these virtualization platforms that you can use to do x86 based you know, simulation and emulation. So, but we've gotten to the point now where we have a lot of good capabilities related to this for embedded systems, which are more in line with spacecraft. So here are 5 examples. So QEMU is an open source free one. It does you know, emulates the machine processor, works x86, Spark, ARM, MIPS, PowerPC, etc. TSIM is one that you can buy commercially that focuses on the Leon architectures. Deja VM, which shows one that we're going to talk about in some subsequent slides, is a whole of system hardware emulation environment. So that's really designed for testing. That's the whole point of Deja VM is testing, and it has a lot of focus on security testing as well. Enables complex you know, systems to be virtualized and integrated in a system-to-system approach. LASIM is a processor emulator built by the Korean Aerospace Research Institute. So they focus on, you know, the ERC 32 and that Leon architecture as well, because that's what they use there. So they have a really high fidelity emulator for that. That's super beneficial if you're working with those platforms. And then Symix is another one. It's a commercial product from Wind River. It's a full system simulator using unchanged, you know, you can run production binaries on the target hardware. Very similar to Deja VM, QEMU, and that type of thing. You can build Leon, RAD 750, PowerPC 750, 401, whatever you want to do. You can build these hardware models using those tools and run the software on it. NASA IVNV, which is where I used to work, has done some great work over the last 10 to 12 years on this front, and has received multiple awards using Symix and other emulators like QEMU. And so they have a long history of proving out this concept of using digital twins for testing in general from an IVNV perspective, as well as some security-based testing. So here's some examples of running, you know, just some core flight software from Goddard Space Flight Center on digital twins. So this is LASIM. This is what LASIM looks like. This is the GR 740 with CFS running on it. So this is a, you know, Spark-based processor. This is Symix running the same flight software or a variation of the flight software in VxWorks on a PowerPC RAD 750. Here's like a lower fidelity model, which is just cross-compiled software for Linux using Docker, using the product called OpenSatKit from NASA. And then this is Deja VM that shows a PowerPC 750 running the core flight software as well. So I've said Deja VM a couple times. What is it? So it's built by Raytheon. And essentially, we're going to have a use case where we used it for some spacecraft research more recently. So Deja VM really helps with the hardware virtualization, and it allows you to rewind, snapshot, replay, and then single step through the assembly code. Supports multiple architectures, x86, ARM, PowerPC, MIPS, etc. It's system of systems. You can have like the full ground as an element. You can have the embedded processor as an element, and it can be software only as fuzzing harnesses you can hook in. Supports multiple guest OS like VxWorks, QNX, Windows, Linux, multitude of ones. I don't have them all listed here. So for our example, for our experimentation and what we were working on, what did we do? We used VxWorks, and we built. So this is a slimmed down version of that reference architecture that I showed. We had ground software using a UDP link to talk to the PowerPC 750 that had NASA core flight software on there that had Deja VM's tools hooked into there, and we had like a network card model to get the data in and out. So that's the digital twin that we're using for this specific subsequent slides here. So the focus of our research that we wanted to do was, can a digital twin be used for advanced cyber testing and zero-day discovery? So can we use these things to actually do the testing that we feel like we can do, which is like find 0 days, find security issues with software. So in our experiment, we attempted to build and model this environment without the source code. So we didn't want to necessarily look at the flight software source. We wanted to look at the binaries. We didn't want to look at the VxWorks source code, for instance. We wanted to use the VxWorks kernel binary and see if we can build out a digital twin just kind of using the binaries. So to do this, you had to get like a disassembler, an extractor, look at hardware documentations like the 750, look for the binaries, which are on GitHub, as well as source code, but we tried not to look at the source code, and look for the design documents as well, if that's available, to help us with the testing and troubleshooting if we needed to. So once the resources have been collected, we performed a basic threat modeling exercise to see to drive our security testing. So what we did was we focused the testing on the interface for the core flight in our digital twin environment, which was the command ingest capability, so the command processing of the software. And then we wanted to focus more at the lower level. So we wanted to focus some testing at the application level, and then we wanted to focus at the hardware design, like lower level PowerPC 750 VxWorks lower level area. And so we did 2 threat models on those areas, and we decided to do that testing. So no real vulnerabilities will be disclosed in this talk. We'll basically just be talking about things that are similar, based on a true story, but not 100% the full things. We're not disclosing vulnerabilities in this talk for various obvious reasons. So why target these 2 areas that we focused on, the command ingest area and the RTOS PowerPC area? So if you look at this this technical operating report 2021-0133 Rev A, Aerospace put out this kind of threat model and threat identification area related to spacecraft. And so there's 40 or so areas, that different layers of the defense in depth stack that you could focus on, and we picked these 4 areas specifically where we wanted to try to see if we could exploit software vulnerabilities or bugs, which is the SVSP1 on the far left here, highlighted in red, as well as affect on-orbit updates, attacking the OS at the OS layer, as well as exploiting things from the ground. So those are the areas that we wanted to focus on specifically. So let's get back to the basics. Let's talk about our first test. We're going to focus, given what we know about the core flight from NASA documentation that's open source, is basically the command ingest area here is where we're going to focus our test. So that's the main interface between the ground software and the flight application in this example. So we're going to focus, so from a generic testing approach, let's focus on the basics. So you identify your interfaces, you choose your testing strategy and tools, you write your test cases, you run your test, analyze the results. So the interface here is CI. The tool we're going to use is Ghidra and Deja VM and reverse engineering tools. We're going to then write our test case, run our tests, analyze our results. So the goal was to reverse engineer and fuzz the target under test to see if we could find a vulnerability with the commanding functionality. The desire was to impact the availability of the spacecraft by crafting a packet or packets that could, that we could send to the spacecraft that could essentially crash the functionality from the ground side. So that was kind of the goal. That was what we were looking to do. And that's what we were successful in doing. So one of the tools we used that I didn't mention yet was we use BlackBerry Jarvis as one of our tools to basically, this is based on DEF CON 2021 talk, which the link's there if you want to learn about using automated tools to reverse engineer embedded binaries. BlackBerry Jarvis was one of the tools mentioned in that talk. So we used it again this year and did some analysis to see if we could find potential issues, and we were able to identify an area that pointed us in the right direction through the automated analysis. We saw there was something within the read uplink function using this automated analysis. So then we loaded it in Ghidra and started to do the reverse engineering and stepping through all those things to see if we could find where an issue could potentially be, and ultimately found an area that we thought looked interesting. And so then we started to work with that area of the code using the features of Deja VM. So Deja VM allowed us to do things in a debugger. We could essentially, hook in, set breakpoints, trying to figure out how a single step through the code and go that route to see what we were looking at. And so that's what we did. So once we basically figured out where we wanted to do the hook with the fuzzer, we started to fuzz that component, that function, using Deja VM's features with the fuzzing harness. So we could basically send data into that function and fuzz it till we triggered some sort of vulnerability. And essentially we were able to find what we called the magic packet, which was a combination of numbers, that would get processed by that function that would cause some sort of crash. So we found it using the fuzzing mechanism within Deja VM. Now let's see if we can actually trigger that from the ground side. So we fuzzed it to find it. Now let's see if we can replicate it from the ground to see if you have the full attack chain. So what we were able to do was send a no-op first, so that we could just show that, hey, look, the satellite is working. A no-op is basically a no operation command. It's like a ping. So we sent the no-op, we got the response, and then we followed it up with the magic packet, if you will. And we saw that we triggered the bug that we were trying to trigger in this case. And depending on your fault management strategy, a bug like this could be hugely impactful, right? Because if you don't have the hardware timer set up correctly or various aspects on the spacecraft, you could potentially, by crashing this application, prevent the satellite from communicating with the commanding. So that area is important. So for interfaces like commanding, obviously you'd want to fuzz and do all sorts of testing on that application so that you don't see something like this. But we were successful achieving our goal in this example. We wanted to see if we could actually trigger a bug from the ground in the interface application that for commanding. So that was successful, and we kind of proved out the concept. So let's recap. What have we done so far? We built a high-fidelity digital twin of an embedded processor, PowerPC 750, using the kind of the sim smithing approach. Deja VM was our use case of a tool. We could have used Kimu, we could have used CMix, we could have used something else, but Deja VM is what we used in this case. We wanted to run the software under test, the operating system, the VxWorks operating system, as well as the NASA Core Flight, which is, VxWorks is commercial, NASA Core Flight is open source. We tried to do that with no source code to see if we could do it, only with binaries, and was successful doing that. And then we reverse engineered the binaries with Jarvis, Ghidra, Binwalk, whatever tools that we could find to use that. Then we constructed the fuzzer and tried to fuzz the read uplink, as well as some items on the software bus within the Core Flight Executive, and was able to figure out where the issue was. We discovered the crash. We confirmed the exploitation from the ground via constructed network packet. So that was a successful use case of discovering a quote unquote 0-day on the command capability of the spacecraft using a digital twin, because we fuzzed it, figured out where the issue was, and then we constructed the packet from the ground, confirming exploitation. So now let's see if we can target something a little lower level in the stack. So right now, what we saw at the application layer, we tested things at the application layer, top of the stack, using digital twin. But can we use this to target things at a lower level? So targeting things down at the real-time operating system level, at the hardware level. Can we target the PowerPC 750 functionality? Can we target VxWorks? Can we target a combination of both using a digital twin to really perform this lower level testing? Because a lot of times what you see with RTOS is the real-time operating systems, or even the hardware layer, the PowerPC, like those are just things that are just accepted as being secure, accurate, free vulnerability. It's been used for a long time. So can we use these digital twins to test those things out? Because we accept these RTOSs will do the thing we want them to do, but will they not? How do they act under adverse conditions? So this is a mechanism to do that testing. So let's go back to the grind where we're actually diving into the details of the user's manual, running things through Jarvis, running things through Ghidra, trying to figure out where we see potential issues and juicy targets to do something. So what we're able to do is similarly leverage the Python or use the fuzzing modules within Deja VM. And we started to consult the design documentation of the hardware and look for quote unquote features that could be exploited to have an impact on the system. Can we use these features nefariously? So you start doing a lot of debugging, a lot of research, a lot of single step, going through the system, setting breakpoints, working with registers, working with memory regions. So it's a lot of exploratory in nature, right? It's a lot of back and forth trying to figure out what's what. And we were able to figure out, okay, let's look at the documentation. We start, writing garbage data and fuzzing certain memory regions. And then what we see is we start getting these weird exceptions in certain areas. And we see machine checks, we see alignment exceptions. So we consult the documentation and see, okay, what is a machine check? And then we start messing with that and going back and forth. Ultimately we find the area that we really feel like could be impactful. And then we basically, after the fuzzing, we go through and go within the Deja VM console. And then we write bytes to the memory region that calls the failure that we were trying to cause based on our fuzzing. And we see that was successful. So to recap, we basically fuzzed a bunch of memory regions and caused different fault conditions and started to inspect the fault conditions to see if we could actually reproduce those. And we were able to do that in multiple ways. Once we figured out the right mechanism to cause the desired effect, which is basically a denial of service effect that we were trying to accomplish, which would kill the system, we wrote those bytes to the memory location that we wanted and had the desired effect. So you can't see this stuff's obfuscated for various reasons, but it doesn't do well in a static demo. But basically, you see the VxWorks exclamation point there in the middle of the screen. That is the exception that gets thrown, and basically the processor's stuck at this point. It can't operate and do anything from that perspective. So we initiated the crash through fuzzing. We confirmed it through kind of manual testing by writing that single packet through. So let's see if we could actually do this from the ground, because that's our goal is can we cause these effects from the ground system? And this we could, because just the way this architecture is designed, the application layer provides direct memory access to the spacecraft, which gave us, kind of unwieldy access to the regions of memory that could have a negative impact on the system. So this is kind of a big deal from the perspective of right now, our systems are designed with this inherent trust between the ground system and spacecraft. And a lot of times the spacecraft doesn't know how to protect itself if the ground system is used nefariously against it. And that's a big issue today, what we see with spacecraft. So we need to make sure we account for that and build in resiliency and protection on the vehicle in the event that the ground system is attacked by an adversary or an insider, once that's very knowing of how to do this type of thing, knows the magic packet to send to do this. So what you see here is basically we sent a no-op command, similarly like we did before, and then to show that we have the receive of the no-op, and then we followed it with the kill pill, the magic packet that disables the functionality that we were trying to disable. And you see that VxWorks exclamation point there, which indicates that the system is now corrupted in a state and it can't respond any longer. So that was a success from that perspective as well. So what about building a full attack chains? Can you do that with digital twins? So if you saw the presentation from 2 years ago that I did at DEF CON 2020 in the Aerospace Village, you'll see there was an example of using digital twin to do simulated GPS spoofing and then other types of attacks. So in that environment, what we're trying to articulate here is you can actually build out these full attack chains, is where you can build, you can mimic the TTPs from the ground side. So the MITRE attack framework there on the left in the middle is, some TTPs that were used to basically attack the ground system to get the foothold, and then you proceed from there to do the rest of the attack and build the full attack chain. You can do that with these digital twins if you have a fully representative environment. You can mimic those TTPs on the ground software, ground system that you're building, and then use those to build attacks against the system. So what you see here is basically a mechanism to tying some of those threats and vulnerabilities from that threat model from that tour to build out an attack chain. So this was basically a way that you could build an attack chain exploiting poor fault management, where you could disable the fault management and disable the security capabilities on the vehicle by jamming the GPS to put it into a safe state, a more clear mode state, where it basically accepts input and disables all the security features that it had. And then you can analyze the traffic that as people are reestablished in comms, and then you can inject packets in that because it's in like a clear text mode, and do things like reset applications or cause denial of service or execute malicious code. So this is an example of trying to build out a full attack chain, because attackers don't basically operate with single TTPs. They string together multiple TTPs, and we need to have these digital environments available to security researchers so they can mimic all those TTPs, because that's what they're going to have access to. If they were to try to attack a real system, they would ultimately have access to the real ground software, the real ground system components, as well as potentially the vehicle, depending on how they're trying to perform the attack. So we need to replicate as much as that in the digital world so we can actually do a lot of those tests. So we must design and test our space systems using this mindset, pulling together. Can my fault management strategy be used against me? Can basically, if someone, from this perspective in this example, right, the fault management strategy was to say, oh, if I ever lose GPS, I won't know where I am. Put me in the safe state, and let's open up the aperture to get comms working again. And that's a really good fault management strategy, potentially, unless an adversary tries to use it against you, where they jam you intentionally just to cause you to go into a fault condition so that they can further the attack. So we really need to understand how attackers could utilize features and vulnerabilities against us and test out these attack chains using these digital twins. And just to touch on the defense in depth area that we mentioned earlier. So if you talk about defense in depth for a space system, how would we be resilient to some of those attacks? Well, you got to build in multiple protections and multiple layers. So the defense in depth has been explained as an onion in the past, where you would have a firewall, intrusion prevention system, authentication, authorization, and hardened configs on a system. So we have at Aerospace, in our tours and our documents have published what we have is like a defense in depth model for ground and space. So on the ground side, this is what that would look like. We have data that backs up these. These are all good principles based on best practices. Cross-correlated with like NIST RMF controls and that type of thing. So these are all good things to do. These are areas of the ground. Similarly, on the spacecraft, we have an equally important defense in depth strategy. So the point is, you're not going to be able to put every one of these subcategories and controls in place. So you got to kind of pick and choose based on your budget, schedule, and risk posture. But at least this gives you kind of a list of things to kind of pick from. And if you want more information on this, go see the tour, cybersecurity protections for spacecraft, the threat-based approach, because we've tied in some of those threat vectors at these layers against the spacecraft and cross-correlated with protections and requirements and things like that. So I recommend going to read that if you're looking to figure out how you do defend and secure these space systems. So in summary, given the kind of the lack of critical space system failures attributed to cyber, sometimes security can get ignored. Now, we did see with the Viasat attack in February during the Russia-Ukraine conflict, that there have been critical space system failures attributed to cyber on the ground. We haven't seen as much on the in the public domain on the spacecraft side, but it's only a matter of time in my estimation. It's not an option moving forward. We need to ensure space systems are secured and have the appropriate testing and engineering resources put in place to ensure they are secure. So because we see these barrier to entries that are being lowered, people can get in the space a lot easier with small sats using commercial services like AWS Ground, as well as commercial launch services. So getting assets into space is a lot easier, which is, expanded the knowledge base on space. And now, people are more educated in the security by obscurity, which was never a valid strategy, is definitely no longer relevant given what we're seeing today with as many people that's moving into the space industry. Also, commonly used technologies, the things that were built 15, 20, 30 years ago were designed way before security was a thing. So we really need to ensure that we have these pen testing, advanced APT simulation emulations happening, and digital twins can be an environment to do that. We need to make sure these commercial entities that we're getting these services from are adequately testing these systems as well. There might not be a requirement, but that is a strong recommendation that they need to be doing the same type of thing where they're testing out, adversary emulation on their systems and trying to see how things can be exploited. From the government side, if you're doing into acquisition, you would definitely want to ensure that digital twins are a part of your acquisition strategy. I would highly recommend as systems are being developed, you're buying, procuring these satellites from vendors, you put in requirements to ensure delivery of digital twins as well. So those are going to be provided back to the governments for security research purposes and things like that. Because no one's going to argue that more testing is not better, in my opinion. So testing is always better. Increasing availability of testing resources using digital twins could be a huge benefit. And as we expand cyber ranges and use of cyber ranges in the space world, we need to really ensure that the spacecraft components are included as a part of the cyber range. So I've seen many cyber ranges across my experience over the last 5 years or more in the government, and some of them are space cyber ranges, but then they have not as much space. It's more ground focused. So when we say space, we say cyber ranges in the space context, we really need to make sure that there's digital twin representative environments for spacecraft and spacecraft technology on that system. So we don't want to just have like a virtualized ground infrastructure. We need high fidelity spacecraft technology in those cyber ranges so that we can do the testing and show the desired effects. We need to normalize red versus blue with space technology. That we need to have more events like the Hackasat event. Hackasat's done fantastic work the last 3 years, educating the public on the importance of security in space, giving access to security researchers to do this type of thing. I can't stress how awesome that is, and we've seen an explosion in the participation over the last 3 years with Hackasat events, and just normalizing security research and getting the word out. It's a big win. So digital twins, software-only simulations can really help further the security research on spacecraft. It's needed. It can help us find the weaknesses and vulnerabilities in spacecraft technology. It can help prove out attack concepts and see what the impact could be, and it can help research mitigation. So if you have a full digital representation and you do an attack and then you have a fix, you can test out the fix, do the attack again, all in a digital simulated emulated world. And one last thing to touch on is, as we do this research and have access to these things and expand on this knowledge base, I think working with organizations like the Space ISAC, which is the Information Sharing and Analysis Center, getting that information distributed on vulnerabilities and issues we're seeing in the space community will be key to educate all the players in this area. So sharing information will be extremely important to outproduce the cyber risk across the community. So with that completes the presentation. I thank you for your time, and contact me. My contact information is on the front slide if you have any questions. Appreciate it.